Thank you very much for the introduction, and Adrien and I are very grateful for the possibility to present here at this discussion meeting, and we'll talk about graphical models for extremes. So extremes, or the extreme value theory in statistics, is concerned with the analysis of extreme events or rare phenomena, which have very small probabilities, but which can still have severe impacts on our health, on the environment, on our economy. And down here you see three examples of such events. So this could be a flood event. Can you see this? This can be a financial crisis, or it can be a severe storm. And this photo actually is of the storm Chiara, which almost prevented us from flying in today. So you see, especially in a changing climate, it's very important to have a proper risk assessment of such extreme events. And now, as a statistician, if we are lucky, we will have data in all of these three examples, and, well, we would like to fit a statistical model to this data. As an extreme value statistician, we're mostly interested in the most extreme events, so the largest values in the tail of the distribution, because they will have the largest impacts in all of these situations. Now, you already see the problem here, namely that we only have very few data points to fit our models, and so we heavily rely on asymptotic approximations or asymptotic results that tell us how this red part can be modeled. And there are basically two possibilities. In the univariate case, it's either relying on the generalized extreme value distribution if we look at block maxima, or at the generalized Pareto distribution if we look at threshold exceedances. And both allow us to compute or estimate high return levels. So here's an example that we worked on a couple of years ago on flood risk assessment in Bavaria in the Danube basin. And at each of these 31 locations where we had measurements of the daily river flow, we can do such an extreme value analysis and estimate, for example, the size of a 100-year flood that can happen there. But this is a purely univariate analysis. So what we plotted here are univariate return levels, and it doesn't tell us anything about the dependence between extreme floods at different locations, whether they occur simultaneously or independently of each other. So often we'll be interested in this dependence because hydro engineers will be interested in constructing flood infrastructure, and it would be useful for them to have simulations on the whole river basin simultaneously. So we're interested in modeling this extremal dependence, but 31 dimensions for extremes is already quite high. So for this reason, one would require to do this properly the notion of sparsity, of conditional independence, and of graphical models. But in the past, these two fields of graphical models on the one side and extreme value theory on the other side have been mostly disjoint. And we'll come later back to the reasons for this. But in this talk, so in the paper that we present today, we're trying to combine these two fields. They actually show that in this intersection, there's a rich mathematical theory and powerful statistical tools that can be applied, and that will later lead to the definition of extremal graphical models.
Hi, everyone. So I will just start by giving a bit of background in graphical models and extreme value theory before seeing how we can combine these two fields. So we assume here that we have a random vector in dimension d with a positive and continuous density. And graphical models heavily relies on notion of conditional independence. And we know that conditional independence between two marginals corresponds to a specific factorization of the joint density. One of the key results in graphical models is Hammersley-Clifford theorem, which gives an equivalence between conditional independence between some of the marginals with the specific factorization of the joint density. So here we assume that we have a decomposable graph in this case. So I will not explain in details what decomposable means, but you can think of a graph that can be decomposed into pieces, namely the cliques and the separator sets. And in this example below, the cliques would be 1 and 2, and a second clique would be 2, 3, and 4, and the separator set would be node 2. And so if we have this graph, then we have an equivalence between the two conditions. The first one We also sometimes say that the random vector x satisfies the pairwise Markov property with respect to the graph. And it's simply that for every I and j that are, for which there is an edge, for which there is no edge in the graph, we have conditional independence between marginal xi and xj given the rest of the vector. And this is equivalent to a specific factorization of the probability density, which can be written as lower dimensional marginals. And so what we want is to, this has been very successful to reduce high dimensional problems, and we want to apply this now, but in our context where we are interested in large values of our random vector x. So just to come back on the example that Sebastian introduced, in this case, the river flows would, so each river station would be one of the marginal of the vector, and we are interested in modeling the dependent structure of the tail of this random vector. And so in particular, if we look at, for example, two stations, station 21 and station 3, in the bivariate case, we would like to estimate the probability of two extreme events occurring jointly on these two stations. So in order to study the tail dependence structure, we introduce a common assumption, which is to assume that the random vector x is regularly varying. And we also assume that the marginals are normalized to be units Pareto. And so we simply separate here the univariate problem. We assume that this is treated separately. And so we only focus on modeling the dependent structure. And so I will now present on the next two slides two different approaches that are used in extreme value theory to study the tail of this distribution. So the first approach is called the maxima approach. And so here we look at independent copies of this random vector x, and we take component-wise maxima, and by assuming that x is regularly varying, under a specific rescaling, we obtain that this converges to a limiting distribution, which is called a max stable distribution. And this max stable distribution is characterized by the exponent measure, which has the property to be homogeneous, as written here. Okay? So one idea that we might start with is to say, well, in order to apply graphical models for extremes, what if we simply assume some conditional independence between the marginal of this random vector z? And in fact, recently there was a result that was very surprising, which showed that when we have conditional independence between the marginal of this vector, it actually corresponds to independence, which means that there is no non-trivial factorization that is possible for the density of max stable processes when the density exists. And of course, well, not of course, but if we don't assume that the random vector z has a density, then some recent work as well have shown that it is possible to define conditional independence and DAGs. But in the case where we are interested today is really the continuous case, because most parametric models that are used for extremes are continuous. So we would like to assume that the random vector z has a density. So because using graphical model doesn't seem to be feasible for max stable distributions, we will focus on the second approach. And the second approach for extreme is called the threshold approach. So here, instead of looking at maxima, we condition on one of the marginal to be large, at least one of the marginal to be large. And as this threshold u goes to infinity, and I remind you that x is regularly varying, this converges to a limiting distribution, and the limiting distribution is called the multivariate Pareto distribution. So two things that I'd like to mention on this. The first is that we have to be now a bit careful because the space on which this limiting distribution lies is this L space here that you can see in the Bivariate case in blue, okay? And so it's a non-product space. And then the second remark is that the class of multivariate Pareto distribution is actually very broad. In fact, it's simply characterized by, if it admits a density, it simply has the property that the density has to be homogeneous, as written here. And remember the exponents measure that I introduced on the previous slide? There is a direct relationship with this. It is that the density of this limiting random vector y is proportional to the exponent measured density. Okay, so now, of course, it is possible to come up with parametric model, for instance, that satisfy these constraints and that are models for a multivariate Pareto distribution. But the problem is that there is no notion of sparsity for multivariate Pareto distribution. And this is exactly what we will introduce now. And so this is what we will do in this section, extremal graphical models. So we will introduce a notion of conditional independence for multivariate Pareto distributions. So as I mentioned before, one of the difficulty here is that we are not working on a product space. And so one way around is to define a series of new variables indexed by the nodes. So for every node k, we define yk to be the initial random vector y, conditioned on one marginal yk to be greater or equal than 1. And we do this for all k. So in the example here, we did it for y1, and in this example, this is done for y2. And now these random vector yk are defined on a product space. And so we will define a new notion of conditional independence for multivariate Pareto distribution as follows. So we say that the random vector, for a random vector that is multivariate Pareto distributed, two marginals ya and yc are conditionally independent given yb if this conditional independence holds for every yk. Okay? And we simply write this notion with a little subscript e for extremal dependence. So simply think of this as a tailor-made notion of conditional independence for multivariate Pareto distributions. So now that we have this new definition, of course, we can define what a graphical model is with respect to this new notion. And so we simply define for a graph G that the multivariate Pareto distribution Y satisfies the pairwise Markov property relative to G if for every I, J, for which there is no edge between them, we have marginal Yi conditionally independent on Yj given the rest of the vector in the extremal sense. And we also say in this case that the random vector Y is an extremal graphical model with respect to G. So just to give you this example here, in this case, if we get a graph, we can directly read the extremal conditional dependence by looking at the graph. And here we can see that, for example, Y1 is conditionally independent on Y3, given Y2 and Y4, because there is no edge between them. Okay, so why is this new notion actually relevant? Well, because now we are able to derive a Hammersley-Clifford theorem for extremal graphical models. And so this goes as follows. We assume that we have a decomposable graph and that the random vector Y is multivariate Pareto distributed. And remember, we also assume that it has a continuous and positive density on this space L. And that the exponent measures that I introduced before are written by lambda. And so the following two conditions are equivalent. The first condition is exactly what I explained on the previous graph. So it simply means that Y is an extremal graphical model with respect to G. And now the equivalent condition is that the density of Y actually factorizes with respect to G, and so can be written as a product of lower dimensional functions. And in fact, these functions, they correspond to the exponent measures that can be thought of as the marginals of the exponent measure, and are defined on the cliques and the separator sets. So I have just two general comments on this result. The first one is that in this case, the graph G is necessarily connected. And this comes from the assumption that we made that the random vector Y has a density. Because we know that when we do this assumption in extreme value theory, we rule out the case of asymptotic independence. And the second remark is maybe that if we look at condition 2, this provides us a way of combining extreme value distributions in a way in low dimension extreme value distributions in a way that the resulting high dimensional distribution is a valid multivariate Pareto distribution. And for the rest, I just let Sebastian continue.
Okay, so now we have seen how we can define conditional independence for these class of distributions, these multivariate Pareto distributions, and we have seen that this is actually a useful notion because it relates to factorizations of densities of these distributions. And now we can actually go back to the literature and look at models that have been introduced and look whether they satisfy these conditional independence properties, so whether they are extremal graphical models or not. And if we look at some classical examples, like the multiple-logistic distribution, the Dirichlet mixture model, or the pairwise beta distribution, we see actually that there are no conditional independencies possible in these models. And this means that their graph, underlying graph, extremal graph, is fully connected. So this somehow also explains why they might not be perfectly suited for high-dimensional inference, or inference in higher dimensions, because they don't allow sparsity. But there's also a class of models in the literature that looks at a very specific kind of graph, namely a chain, so which I wrote here. And actually people have thought about this and have constructed extreme value distributions on this simple graph by combining bivariate distributions. And these extremal graphical models also arise in the study of stationary Markov chains as the limits of extremes of these chains, and they are called the tail chains. And this means that the notion that we introduced of extremal conditional independence, extremal graphical models, is kind of natural because it kind of fits very well in the existing literature here. So, but these chain graphs are very simple graphs, and some are very limited in terms of flexibility. So the next thing we can actually do with our theory is to go to more complicated graphs. And the next step after chains would be to look at tree graphical models. So a tree is simply a connected graph without cycles. So all cliques in this case are have two nodes, and the separator sets consist of single nodes or singletons. And in this case, the Hammersley-Clifford theorem that we showed before says that the density of the corresponding multivariate Pareto distribution that factorize on this tree factorize into a very simple form, namely in a form where we only have bivariate and univariate distributions. So we have these bivariate exponent measure densities, lambda ij, and the univariate distributions, because of normalization to Pareto distributions, are simply given by y to the minus 2. And this means that this doesn't contain any parameter that we would have to estimate. So really we just have these bivariate distributions that we can use to construct models on tree extremal graphical models. And recently it has also been shown that these tree extremal models are the limits of regular varying Markov trees. So this is a recent paper. Now we'll look at a very important example called the Hüsler-Reiss distributions, because it will allow us to go to more general graphs than only trees. And you can think of this class of, it's a parametric class of distribution, you can think of this as the Gaussian distributions in extremes. And you'll see on the next slide why this is the case. Hüsler-Reiss distributions are parameterized by a d times t variogram matrix. So a variogram is a conditionally negative definite matrix. It's somehow similar to covariance matrix, but not exactly the same. I don't want to go in details here. So once we have this parameter fixed, this parameter matrix, the density on this L-shaped space of the Hüsler-Reiss distribution is given by this form here. And you can see here we have to fix a root node k. This is arbitrary but fixed. And in fact, the right-hand side does not depend on the choice of k, even though it looks like it does. And well, we see that this density is basically a transformation of a d-1 dimensional normal density with a particular covariance matrix, which is given down here as a transformation of the parameter matrix gamma. And well, we can, as I said, we can do this for any k, but it's important to note that this, this normal density corresponds to a d-1 dimensional normal distribution, and so also this covariance matrix is d-1 dimensional. And this means that we cannot directly read off conditional independencies from this matrix, but things will be a bit different as in the Gaussian case. Because if you remember, in the Gaussian case, we could simply look at the inverse of the covariance matrix or the precision matrix and read off the conditional independencies by zeros on this precision matrix. So we would like to have a similar result for this class of Hüsler-Reiss distributions. So we recall this, this covariance matrix that appears in the density of the Hüsler-Reiss distribution, and we define now the inverse of this, if it exists, and well, this we can call a precision matrix, and again we recall it's d-1 dimensional. So now if we start with a d-dimensional Hüsler-Reiss distribution on some d-dimensional Hüsler-Reiss distribution with parameter matrix gamma, then we can show the following. We know that the conditional independence of the ith and the jth node, the conditional independence of the ith and the jth node, given the remaining variables, in our extremal sense, is equivalent to the following. And here, there we have two different cases. If I and j are not equal to this root node that we chose, then we can just look at zeros in this precision matrix theta k. But if one of these nodes, for example, the ith, is equal to the root node k, then we have to look at something else, because we recall that this matrix only has d-1 dimensions, but we have a graph with d nodes. So there we have to look at the row sum of the jth row. In order, and if this is 0, we know that there is conditional independence of the kth and the jth node. Okay, so this is a bit different than in the Gaussian case, but at least we know that with these, all these precision metrics theta k, we can read off the complete graph structure from just this one matrix. I'll try to make this a bit more clear with an example. So here we have a graph, and you already see this graph is not decomposable. So this is actually possible because the result on the previous slides holds for general graphs. So there we don't need the decomposability assumption. Okay, so I have, we fixed this graph, and I define a parameter matrix gamma for this Hüsler-Reiss distribution. And this I did somehow in an arbitrary way. And we'll now see that this actually corresponds to an extremal graphical model on this graph. So what we have to do is we fix a root node k, say the second one here, and then we compute this matrix sigma k as a transformation of gamma, and then we take the inverse of it. So we have the precision matrix theta 2 in that case. And now we see, well, the second row and column are deleted, right? So we have only d-1, see three rows and columns. And we see 1, 0 here corresponding to the first and fourth entry, or first and fourth variable. That means there is no edge between node 1 and 4, and this is exactly what we see up there in the graph. Otherwise, there are no zeros, but we know now if we're interested in connections or edges that relate to the root node, so the second node here, then we have to look at the row sums. And we see that, okay, the first row sum is not equal to 0, so there should be an edge between 1 and 2. This is the case. The third row sum is equal to 0. So if we sum up this two negative 0.5s and 1, it gives us 0. And this means that there should be no edge between the third and the second, so the root node variable. So this is exactly what we see. There is no edge. And then again, the fourth row is again not 0, the row sum, so there should be a connection between 2 and 4. So that means we can read off of this precision matrix θ2 in d minus 1 dimension the whole d-dimensional graphical structure, extremal graphical structure. Now you might wonder what happens if we change the root node. So we choose, for example, the third variable as a root node. Of course, the numbers now change, but if we do this whole exercise again, we'll recover exactly the same graphical structure again. Okay, so each single precision matrix contains all the information on the extremal graphical models. So we are free to choose whichever we would like. Okay, so now these were more the probabilistic results. Now I'll come to how we apply this for statistical inference to construct statistical models. So here we restrict to the case of so-called block graphs. Block graphs are decomposable graphs where the separator sets are single nodes. Okay, so for example, here we have click 1, 2, click 2, 3, 4, 5, and click 5, 6, 7, and the separators are just the node 2 and the node 5. So these are both single nodes. And this has the advantage that we can construct higher dimensional models from models on these lower dimensional clicks. So for example, we can choose parametric families on each of these clicks and then combine them. So we choose these exponent measure densities and choose a suitable parametric family, whatever we like. And then we know that all the separator sets are singletons. That means the density of the separator sets are exactly this y to the minus 2, so the density of a Pareto distribution. And then from our Hammersley-Clifford theorem, we know that if we combine the lower dimensional click densities in this way here, then we get a valid d-dimensional density for a multivariate Pareto distribution. So we're very free what we do on the clicks, and then just multiplying them together gives us a higher dimensional density. This also includes trees, for example, as a special case. Now the question is, how can we estimate these models? And likelihood inference in extremes is very challenging for several reasons. And one reason is that usually we will have to censor our likelihood on observations or components of the observations that are not extreme, and that introduces a numerical integration, which is usually quite slow to solve in higher dimensions. So, but still in low dimensions, we can use the full joint likelihood. So we suppose we have data YH or n data points of this random vector y, so of the multivariate Pareto distribution, which usually are obtained as approximations by threshold exceedances of our vector x in the domain of attraction. And well, our joint likelihood looks like this here. We know that the likelihood, because it's a likelihood on a block graph, factorizes into the product of the likelihoods on the clicks. And we have a normalizing constant that might depend on the parameters. Now, well, okay, we can use this, and as I said before, typically we want to censor this likelihood, so we have an additional numerical step where we have to integrate out certain marginals that are not extreme, and that makes the whole thing very slow in higher dimensions. So low dimensions are applicable, but in dimensions larger than, I don't know, 5 or 10, this becomes completely infeasible. So we have an alternative to this. This is what we call the click likelihood. We'll estimate the parameters corresponding to the different clicks separately. So here the parameter vector contains the subparameters of the corresponding to the different clicks. And we estimate now these click parameters by simply optimizing maximizing the log likelihood that only come from the contributions on that click and from observations that are extreme on that click. And this is much more efficient numerically because we actually have much smaller dimensional densities. If we do numerical integration for censoring, it's much, much faster than using the whole likelihood. So This estimation here of the parameters of the parametric model assumes that we know the underlying graph structure. But in many applications, of course, we don't know what the underlying graph structure is, and we have to estimate it from the data. So one simple thing, or one first step that we can do, is we can try to estimate a tree structure as a first approximation. And there is this minimum spanning tree algorithm that is used in these cases. And the question is always which weights we use in this minimum spanning tree algorithm. And here we propose to use what is called a maximum likelihood tree, or a Chow-Liu tree, where we put on the edges as weights the negative log likelihoods of maximized bivariate distributions. And here we have to choose a parametric family for these bivariate distributions, such as Hüsler, Reiss, or logistic. And then we can optimize all of those bivariate distributions, put these as the weights on in a minimum spanning tree algorithm, and then get back what is called maximum likelihood tree. So this is how we can obtain a tree from the data. Now, the tree might not be flexible enough. We would like to have a more general block graph. And we can do this in the following way. So we can start with this estimated tree, or with another tree that we maybe have from domain knowledge. And then we can add additional edges to make this graphical model, extremal graphical model, more flexible. And, well, we do this adding of the edges in a greedy way. And yeah, we do forward selection and base our choice on the AIC. So like this, we can, starting from a tree, get more and more complicated graphs until we are happy with the flexibility of that model. So I'll now show you how this works in simulations and in the application on the river data that we've seen before. So here, just a very small simulation study. We simulate from a Hüsler-Reiss graphical model on this particular graph here, which is a tree in that case. And we only have to specify the parameters on the edges of that tree, so only 4 parameters. And the other parameters are then implied by the conditional independent structure. Okay, so I put those in gray here. Those parameters we don't have to specify, but they are directly implied from these 4 parameters that we specified. And we simulate 200 samples from the limiting distribution y, and then try to estimate the parameters. And now we only have to estimate these 4 parameters, because the other ones are implied implicitly. And we use the full likelihood on the one hand side, which still is possible in this dimension, and the click likelihood on the other side. So here just some results. So in orange we have the joint likelihood, and in blue the click likelihood. And we plotted the box plots of the errors of these 4 parameter estimates. And we see that we don't lose a lot of efficiency by using the click likelihood compared to the joint likelihood. And this comes from the fact that we're actually working with graphical models. And this kind of factorization into the clicks is very natural. And so, we're not losing a lot of efficiency here. And also in higher dimensions, as I said before, this will be the only choice, because the joint likelihood is no longer possible to apply because of the censoring step. In the paper, we also have other simulations with different sample sizes, and we also show that we can recover the true underlying tree structure when estimating it from the data. Or not only tree, but a graph structure when estimating it from the data. Okay, let's come to the application. So this was this example of river flows in the Upper Danube Basin. So here we have 31 dimensions, and we're measuring daily discharge at these 31 stations. And we have to decluster the data in time to get independent events. And we get 428 declustered data points, x1 to xn, in a time frame from 1960 to 2009. And those we can now use to estimate our graph and to estimate the parameters of our model for the extremes of these river flows. So in this particular example, we have an underlying physical tree structure, right, given by the flow connections. In some sense, it is not necessarily the true underlying structure or graphical structure for our statistical analysis, because it might be that there is another graph that gives us better result for statistical analysis, but still interesting here to compare to this graph. Of course, this will have an influence. The flow connections will have a strong influence on dependence. But there might be other effects, like spatial rainfall patterns, that affect things that are not flow connected. So we propose a sequence of different models. So we stay in the class of Hüsler-Reiss graphical models, but we could also work with different models, with asymmetric models if we like, or even non-parametric models. But here we stay in the class of Hüsler-Reiss graphical models, and we start with G1 is the simplest graph is a tree, and we can start with two different trees. One is the maximum likelihood tree, and the other one we can take as the actual tree coming from the flow connections that we have because of domain knowledge in this application. But if we had not this domain knowledge, we would have to start with a maximum likelihood tree. But here, just as a comparison, we can start with this physical tree. And then we do this greedy forward selection where we add additional edges to that tree in both cases, and then get a sequence of models that become more complicated and have more edges, have more parameters. So here just some results. So first let's look at the blue curve. So the first point there has 30 edges. So the first model has 30 edges. It's a tree because we have 31 stations. A tree on 31 nodes has 30 edges. And once we add more and more edges, we see that the AIC for this model is going first down, and at some point it's going up again, meaning that we have reached a degree of sparsity that is flexible enough for this data. We can now also look at the black curve. Here we start not with the maximum likelihood tree, but we start with a physical flow connection tree. And we see, of course, by definition, for the tree, this model is worse than the maximum likelihood tree. But once we add more edges, somehow surprisingly, the AIC goes below the AIC of the best model on the blue curve. But this can happen because this forward selection is a very greedy procedure, so we're not guaranteed to reach the global minimum with this. So in this case, it seems that if we start with a different tree that also makes a lot of sense now physically, that we get a better model in the end. It's also interesting to compare this to the model that we constructed in the 2015 paper. This model was completely different. It was not using any sparsity or not using any graphical models. This was more like a geostatistical spatial extreme value model. And we see that the AIC of this model is better than the tree models, but it's not as good as the optimal graphical model. I should also mention that in this case, we used a lot of domain knowledge, like the catchment sizes and the structure of the river network and so on. So we had to work quite hard to make this work. And in the graphical approach, we don't need this domain knowledge. We can estimate, in principle, the graph from the data and can apply this then also to situations where we don't have any information on the underlying networks. Okay, it's also interesting to compare the estimated graph structures. So on the left is the physical tree, and on the right is the best model in terms of AIC. And we see that in addition to this tree structure, we add edges that connect nodes that might have a strong dependence, even though they are not flow connected, but they might have a strong dependence due to, as I said before, spatial rainfall events that affect both of the catchments corresponding to these stations. And the graphical model would like to introduce additional dependence not being explained sufficiently with the physical flow connection structure. So how much time do you have? 5 minutes? Okay. So another way of checking our model fit is a so-called extremal correlation, which is a bivariate summary statistic for extremes. You can think of this as like the analogous way of correlation, of measuring correlation, but for extremes. So basically, this extremal correlations chi ij between station ij is given by the probability that we see an extreme event at station j, given that we've seen an extreme event at station I. And well, this is so if this is close to 1, it will tell us that there's very strong dependence between the extremes. If it's close to 0, then there's a very weak dependence. And we can estimate this coefficient empirically and then compare it to the model fit from our graphical model or from the spatial model from 2015. And here the blue points correspond to pairs that are flow connected, and the black points correspond to pairs that are not flow connected. And we see that both models fit this data quite well in terms of this bivariate measure. Maybe even the graphical model has a bit less bias, but yeah, in general, those two fit very well. But we know that for this whole joint distribution, the AIC of the graphical model was lower. I mean, this is just a summary in terms of bivariate summary statistics. So, okay, let me conclude. So we have shown that with these extremal graphical models, we have a tool for risk assessment in fairly high dimensions by breaking down complicated dependent structures to lower dimensional clique likelihoods and dependencies. And, well, the very important point here is that we're not required to know a lot of domain knowledge, but we can estimate the underlying structure by using the data. And, well, the estimated graph, and this is very good for practitioners, can be used directly for interpretation. So as we've shown, the estimation can be performed efficiently because of that graph structure on these lower dimensional pieces of the graphs, the cliques. And this makes especially likelihood inference feasible in higher dimensions compared to this joint likelihood that is very limited quite quickly if we even talk about moderate dimensions. I haven't talked about simulation from these models, but we can show that, and in the paper we show how we can do exact simulation using the theory of extremal functions of any extremal graphical model. So we've also implemented these methods in an R package that you can find on CRAN. For example, there are methods to transform this Hüsler-Reiss parameter matrix to the precision matrix and to directly get the graph structure, to estimate the tree and block extremal graph structures, and to simulate from them. So we really see this work here as like the first step in exploring this marriage between extremes and graphical models. And there are many future directions that we have partly already started thinking about, but I think partly also not yet thought about enough. So one example is this learning of the underlying graph structures. In this paper, we've really just touched upon this topic with this maximum likelihood tree and this greedy algorithm. But in fact, now we have already seen that learning tree structures can be done in a much more general way by just using non-parametric estimates of the extremal correlation. And we can actually show that solving this minimum spanning tree problem, we can estimate the true underlying tree structure without any further assumption on the parametric form of the bivariate distributions. And this is somehow surprising because in the non-extreme case, we have to assume Gaussianity if we want to have a similar result here using correlation. Then for Histlerized distributions, so this parametric class that are the Gaussian distributions in extremes, we can even do more. We can use this result on the sparsity in terms of the precision matrix to do like a graphical lasso type estimator by L1 penalization of the densities to estimate automatically the right amount of sparsity in these Hüsler-Reiss graphs. There's also connection of these graphical models once we make them. So this was all about undirected graphical models, but we can make them directed. And then there's a connection to causal inference and in connection with extremes, which is a very active research area at the moment because people are interested, for example, in climate science to find out what the attribution of human activities on the climate are, and especially on climate extremes. So there's a very active area, and there are already some first results in this direction. So to finish, I want to say this is an active area, and there are many open problems. So I have an open PhD position and 2 open postdoc positions on this topic. So if you're interested, or you know someone who might be interested, please let me know, or you can find more information on this website. I'd like to thank you for your attention.
So I'd like to start by saying congratulations to Sebastian and Adrien on a really nice piece of work. I think the paper is very rich in new ideas and very elegant detail, and it was really enjoyable to read, so thank you. So the setting of the paper is that of multivariate regular variation, which at its heart is a regularity assumption on the extremal dependent structure of a random vector. So stripping out the effect of the marginal distributions, multivariate regular variation implies a couple of different related important convergences. So firstly, convergence of the distribution of normalized component-wise maxima to a multivariate max stable distribution, and convergence of the distribution of suitably normalized threshold exceedances to a multivariate Pareto distribution. And both of these limiting distributions are governed by the same quantity lambda, which is this exponent measure. So lambda encapsulates all of the extremal dependence information in these representations. Now, multivariate regular variation as an assumption holds very broadly, but it doesn't always necessarily lead us to interesting dependent structures or necessarily is helpful for statistical modeling in all cases. So for example, if lambda is equal to a sum of the reciprocal of the components of z, then this implies mutual independence between the component-wise maxima and leads to quite a strange-looking multivariate Pareto distribution. So in order to avoid these kind of situations in the paper, the authors make some extra assumptions. So they suppose that densities exist, which is normally quite reasonable for statistical modeling, but they specifically also suppose that the d-dimensional exponent measure density exists. So this little lambda is positive. And what this means is that there's essentially a positive probability that each of the d components of this underlying random vector can be simultaneously extreme. So it's a really quite a strong form of underlying extremal dependence which is assumed. So the paper is very rich in content and makes lots of key contributions, and in particular the main one is exposing how results from the world of graphical models pass through very nicely to the world of extremes via the density of the exponent measure. And in particular, how these, the density factorizes and how we can interpret these factorizations according to graphs and interpret the graphs with respect to certain kinds of conditional independences. There's some really neat results on the Hüsler-Reiss class of distributions, so showing, as we've just seen in the talk, how parameterizations of these distributions in terms of precision matrices and the zeros in those precision matrices link to the extremal graphical models. They also show us how we can construct coherent high-dimensional Pareto models via lower-dimensional ones in certain cases, and in special cases, how we can do inference on just lower-dimensional ones without much loss of efficiency. And whilst it would be very nice if the graph was just given to us, obviously that's not going to be the case in general, so they start to address what's a very important question of learning this graphical structure from the data. We also get quite a lot of additional insight into the concept of extremal functions in the paper, and that's become an increasingly important concept in recent years related to simulation of max stable processes and Pareto processes and the multivariate counterparts. And generally, I think one of the things I like the most about the paper is that it works very nicely at the big picture level, so it's giving us a whole new idea and a whole new set of tools, but it also works really well at the detailed level. So there's a lot of interesting individual results which are of independent interest and can be used in different contexts. So one thing I found quite intriguing about this paper was how it links quite nicely to what I think was the last RSS discussion paper in extremes by Jan Heffernan and John Thorne in 2004. And this link comes through the key role that's played by this random vector yk and the extremal function uk. So in the setup of this paper, we can actually directly derive these extremal functions through a convergence on the underlying random vector x. If we condition on the kth component being large, normalized by that kth component, then we get convergence and distribution to the extremal function uk. And this is exactly the type of thing that Heffernan and Thorne were looking at in their 2004 paper. Okay, so the logs appear here because in the Heffernan and Thorne paper they worked in exponential tail margins as opposed to heavy tail margins. Okay, so unsurprisingly, as they should, they found exactly the same kind of distribution there. But why do I bring this up? Well, I bring this up because the act of conditioning specifically on one component being large as opposed to conditioning on, say, the maximum being large allows us to think about convergences which can accommodate different strengths of extremal dependence between the different components of the random vector. And this potentially frees us up from having to think about extremely strong extremal dependence between all of the different components. So it suggests that maybe there's some kind of utility in considering the so-called conditional extreme value theory approach in this context. Okay, so in full generality, this is what the kind of convergence assumption in the conditional extreme value model looks like. So we condition on a single component being large, and then we suppose that we can find functions ak and bk such that when we linearly normalize the rest of the vector with these functions, we get convergence to some kind of non-degenerate limiting random vector. So this certainly covers the setting of the paper, where thanks to the sort of strong dependence assumptions, we know exactly what the form of the A and B functions are, and we know in this case that we get the zk's that we get out. These are just transformations of the extremal functions, and we know, thanks to the work in Engelke and Hitz, how these give us graphical structure of Y, if there is graphical structure to be had. And the reason that we can translate from one conditioning variable to another is because we have this positive exponent measured density, which essentially provides the glue that binds all these different distributions together. So in the more general case, we can still get interesting limits, even in the situation where this exponent measured density is null. But the price we pay for that flexibility is that the characterization of the limits is generally more difficult in this case. And that's because this null exponent measured density means that the glue which binds everything together is broken. Nonetheless, I think this still suggests two possible extensions for statistical inference. So the first is, well, for the Hüsler-Reiss model, we can directly access realizations of zk, which are supposed to be multivariate normal, and which have covariance matrix equal to sigma k, using the notation from the paper, and exploit more traditional graphical modeling techniques to learn about the structure in the data. And I think that's possibly what Sebastian was hinting at on his final slide. In the more general case, we could also potentially consider graphical structures of these vectors zk. Now, it's less clear necessarily how they will link to a global graphical model, but we might still learn something interesting about the data, and in particular about these functions ak and bk if we can parameterize those. So I briefly coded something up in this line, but I don't think I actually have time to talk about it too much. So hopefully I will squeeze this into the written version of the discussion instead. So I just want to conclude with a couple of comments. The first is that I really appreciate the mathematical niceties of the framework, and they were absolutely necessary for all the results that came out of the paper. But I think it should be acknowledged that the setting is at some level practically restrictive. So even if we have that this exponent measured density is positive for a d-dimensional set of variables, then if we add in a new variable, we need that this new variable is still very strongly dependent with all of the existing variables. And this sort of highlights that there's a natural tension between methods that we have now, thanks to this paper, which permit high-dimensional model construction, and the unfortunate fact that high-dimensional data are less and less likely to adhere to these strict conditions. Nonetheless, the paper here has still spurred me on to think about possible structured estimation for more general extremal dependent structures, and I'm sure it's going to generate a lot of other interesting follow-up work. So to sum up, I found it a really fascinating paper, and it was really a pleasure to read, and it's a great pleasure to propose a vote of thanks. So thank you.
First of all, let me congratulate the authors for this thought-provoking and extremely elegant paper. I would like to open this discussion by, for the sake of history, with some remarks, some historical remarks, effectively mentioning that there have been several attempts in the past to bring the two worlds together, the world of graphical models and extreme value theory. And the implication for bringing these two worlds together equals to immense benefits for statistical modeling of extreme values. So it was basically the doorway to high-dimensional inference and building scalable models. So this was realized by key figures in the field, and results were scattered around for more than 2 decades. So I think it was first Richard Smith, and then later on Smith, Stuart Coles, and Jonathan Thorne, who had the first results on graphical structures in extremes. But until Engelke and Hitz, there was no formal mathematical underpinning theory bringing the two worlds together. So one thing that was known was that actually the spectral density can factorize, yet some results were quite unfavorable. So together with Kirsten, we effectively proved that any max stable distribution with positive density cannot embody meaningful or useful conditional independent structures. So that was quite unfavorable, but it was realized that a natural way forward to building graphical structures is through the natural consideration through condition limit laws, and we set out on a quest to understand limit theorems under specific graphical structures, normally those induced by stationary processes through conditioning on extreme components. So Engelke Hitz attacked this problem in a quite different way, and in particular they set out to introduce graphical structures in the world of fully asymptotic dependent extremes. So the setup of the paper is for a vector x to be in standard Pareto margins, so we're no longer thinking of the margins here, but just the dependent structure. And the approach adopted was moving away from that of standard multivariate variation and that of component-wise maxima, but instead looked at the most natural approach, which is threshold exceedances approach, where the appropriately scaled vector x, given its maximum exceeding a large level, converges to a multivariate Pareto distribution, this bold y. So that means basically that the probability distribution function here has a specific form, so it's given in terms of the exponent measure capital lambda, where the authors do assume for both for technical reasons to set up the new framework. It has density on the interior of the cone E, which imposes quite severe dependence forms for this particular dependence model. In particular, having a density in the interior implies that all components of X can grow large at the same rate. However, one of the key contributions here is that actually the density of the multivariate Pareto is basically proportional to the density of its exponent measure. And just to go to the contributions of the paper, what I would like to say here is that Engelke and Hitz effectively went beyond the standard component-wise maxima approach and restricted or defined meaningful conditional independent structures by restricting on product spaces of the support of the multivariate distribution. So the key structure was derived from the behavior of bold y, given that its kth element is larger than 1, and that's clearly supported on the product space Lk, which is written there. So the problem was attacked through, this conditional extremes convergence. So given that one element is large and rescaling appropriately the vector x by this particular element, we have convergence to this conditioned random vector on the product space. And there we can have conditional independence. We can actually require conditional independence there, which permeates throughout the entire support of the multivariate Pareto distribution. So it's quite important here to bring up the relationship with the previous discussion paper on conditional extremes by Heffernan and Thorne, which is a more general case that allows different strengths, different dependent strengths between components of the random vector in this specific fashion here, where we have additional parameters, bold alpha and bold beta, that in the paper were assumed to be a vector of ones and zeros respectively, that allows us to have a richer framework. So, to sum up the contributions, one thing I really found important and is likely to spearhead the way we construct models in extremes is this natural definition of conditional independence, where, for a multivariate Pareto, Engelke and Hitz mentioned, that admits a positive and continuous density, we say that sets YA and YB are conditionally dependent given set B if we have this conditional independence restricted on the kth element being large. So this has an immense consequence. So it allows graphical models for threshold exceedances through the factorization of the Pareto density. So Fy here takes a specific form for decomposable graphs. And one key contribution is related to a specific structure in Hüsler-Reiss distributions, where the author showed that we can actually identify conditional dependence through the specific precision matrices that relate to the parameter matrix gamma of the Hüsler-Reiss. Moreover, there is likelihood-based inference allowing us to do model checking and selection, so this is a great advance. I would like, though, to bring up some limitations and response to criticism. So that has been brought up already, but I think the key issue here relates to scalability. So this strict form of dependence effectively rules out independence, or it can rule out asymptotic independence, where components can have different strengths, or dependence of extremal dependence. So the implication of this is actually that the graph has to be necessarily fully connected and cannot facilitate for these more practically useful forms of dependent structures. So the question here is, isn't it still early to talk about truly flexible high-dimensional inference? Another point I would like to bring up is by designating this conditional independence symbol, Philip David symbol, do we really need to associate it with multivariate Pareto name? To be more specific here, I would like to respond to some of the criticisms that were brought in the paper in relation to the general conditional extremes framework of Heffernan and Thorne, where the authors state that therefore there are no problems with lack of self-consistency, as for instance in this model. So what I would like to rectify here is the general conditional model. So a Heffernan and Thorne model can be written as a dynamic mixture model. So if you have an arbitrary joint density indexed by k as a kth mixture component, then a conditional extreme value model, which models this particular distribution, is taking this specific form. So it's a weighted mixture of these joint components, each of which is defined on these LK shapes. So for k equals 1, we are restricting to this L1 shape, whereas for L equals 2, we are restricting to this shape. So just to show some animation here, so in the usual framework of conditional extremes, we approximate these joint densities by limiting forms, which are not necessarily consistent. Yet, what this particular mixture representation allows us to do is simulate on these particular quadrants here, where this is the traditional Heffernan-Thorne model, that in this particular space here it gives a weight 1 for the conditional 1 and 0 otherwise. So you see that some points are going to land on top of x equals y line, getting rejected. So continuing in this fashion and changing the margins, we are we are effectively sampling from this region. So we are sampling from a valid probability measure, which has self-consistent marginals. So a quick thing to stop here is that the authors allude to, potentially allude to the limiting conditional distribution not being self-consistent under asymptotic independence, but the model ensures both consistency at subasymptotic levels and inconsistent limiting distributions which are compatible with theory. So does it really matter if the limiting distributions are inconsistent? So I'll stop here, and I would like to say that the paper leaves open important problems, and there is still much work to be done, but plenty has been done by Sebastian and Adrien. It is with great pleasure that I second the vote of thanks for what will be, I'm sure, a very influential paper. Thank you very much.
I'd like to congratulate both authors to this. Actually, I think it's sort of paradigm shift in high-dimensional extremes. It's first time it brings together graphical models and extremes in a, I think, meaningful way that can lead to a lot of future interesting research. I'm not going to talk about future directions. Actually, I'd like to come back to an issue that has also been mentioned by the previous vote of thanks. So namely that the model itself might be a bit restrictive in the sense that the exponent measure is supposed to be only on, well, it is on the upper orthant, but it is supposed to have a density on this upper orthant. That has consequences in the sense that the components of the vector that we want to study cannot be extremely independent, so it excludes some structure that we usually have available in multivariate extremes. And on the other hand, it also means that this definition of extremal independence cannot be extended to the case of independence. So we have the conditional independence, but not the independence included, so the empty set doesn't really make sense. Which leads to the situation that the graphical models resulting from this always have to be disconnected, basically. So we don't, so the proposed model doesn't embody this disconnectedness at present. So this was a question that was lingering in my mind, and I wanted to resolve that somehow for myself. And I'd like to remind ourselves about the structure of this upper orthant on which this density is defined. In the case of 3 dimensions, we have one-dimensional faces, 2-dimensional faces, and this 3-dimensional inner face. And if we want to complete the model, what we have to do is we have to allow also, for instance, densities on these subfaces, or at least the measure to have mass on all of these subfaces. And that means that we have an old notion of extremal independence, which can be defined in terms of the exponent measure. So it's quite universally agreed among extremes people that we have, that we say that things like that this can be phrased in terms of where the exponent measure puts mass, basically. And now that we can also make sense of in this new way that Sebastian and Adrien defined for extremal independence. So it makes sense to extend this notion to the case for the empty set. And we can ask ourselves, how are these two notions actually related? Are they the same? Does one imply the other? And I'd like to give an answer to that today. So, first of all, the old notion implies the new notion of extremal independence. So let us look at an example. Let us say we have only a 3-dimensional vector and we decompose it into the first 2 and the third component. And the old notion of extremal independence in that case means that the exponent measure has these faces here as support set. So only things are allowed where we are, the index sets are subsets of A and C. So this is the case And if we want to prove that the new notion of extremal independence holds true in this case, we have to consider these vectors y and on these half spaces where this is this product measure is well defined. And we see here indeed, if you look at the intersection, then this splits. So this splits as a product measure where one component is degenerate. So this establishes the new notion of extremal independence in the case k equal 2, but we can check that for actually any situation. And the next good news is the new notion also implies the old notion. The proof is a bit more complicated because for the new notion of extremal independence, we have to make use of all these product measure splittings here, so on all these half spaces that translate into a particular structure of the exponent measure that they factorize. And now we can look at the intersection of all these green spaces here, these half spaces. And on the intersection, we see one can prove that if this is a non-trivial measure on the intersection, then this has to split according to these splitting measures. Thanks. And this is a contradiction to the homogeneity. It implies old extremal independence, and so the good news is it's possible, it's meaningful, and it gives us disconnected extremal graphs. Thanks.
I'd like to, like the other speakers, I'd like to congratulate the authors of this paper on a very nice piece of work. It's a double pleasure because both of them know, well, not this logo, but the previous logo of EPFL very well, having been there. There's some good things, lots of good things in the paper, as the previous speakers have pointed out. There's this elegant extension of the Gaussian graphical models. There's the use of multivariate threshold exceedances, which means we're really modeling individual events, and that makes inference simpler because they're somehow based on generalized Pareto models. We don't muddle up maxima as happens when one looks at the analysis of multivariate, even univariate block maxima. And there's this potential that Sebastian alluded to at the end for application to settings for causal inference. There's limitations which have just been demolished, some of them, by the previous discussants. The graph must be connected, except maybe not. One point made in the paper and in the applications, one seems to be limited to rather small cliques, and I think this is potentially a serious difficulty. As already mentioned, there's this issue of asymptotic dependence. And also the data are likely to be limited, and so is it really possible to estimate very complex models in such settings? That relates back to this issue about, to the use of multivariate threshold exceedances, because it's unlikely that everything will be large all at once, and that tends to mean that the information available for estimating the very graphs with big cliques will be limited. I'd just like to bring up one point that's not mentioned here on the slides I prepared, and that is this issue about the fitting likelihoods for rather small models. As I guess the authors know, but maybe I should remind them, Raphael de Fondeville has done work where he uses the gradient score rather than likelihood estimation, and is able to work in very, very high dimensions, thousands of variables, particularly in contexts where one's got radar data, say, and he's able to fit relatively low-dimensional models, admittedly, but to very, very large data sets. So I think maybe the likelihood is possibly a slightly blind alley here, that one could do things rather better. What I want to talk about mostly is the application of these data in work by Charlotte Darnay to data on negative daily returns for some banks over the period 2001 to 2018, using a threshold at the 0.95 quantile of the marginal distributions. When not using the package, we couldn't get it to work, but I'm sure it's better now. But so doing her own coding, Charlotte generated the graphs you see here. On the left, you see a minimal spanning tree for 22 different banks. We're looking at extreme days where there are extreme negative returns, bad days for banks, or bad days for people with stocks in banks, investments in banks. And on the left, you see the minimal spanning tree generated by the Kruskal algorithm described in the paper. And you can see that banks 4, 18, and to some extent 9 over there are somehow links. And these actually relate to Santander, Deutsche Bank, Credit Suisse, and JP Morgan. If we look at the right-hand graph here, the network, we see on the blue banks, the blue blobs correspond to US banks, and you can see that some of them have become cliques of size 3. The green ones correspond to European banks, and the grey ones correspond to rest of the world. Thank you. And there you can see that those are attached, in some cases, to rather strange connections. So I suspect here that Charlotte did her best, we did our best, but the connections don't seem to be very clear or very natural in some cases, and that may be because of the restriction to rather small cliques. One might expect to see much bigger cliques in this setup. If we look before and after the crisis, before and after 2008, this becomes even clearer in some way. Some structure remains constant. Credit Suisse and UBS are rather similar, same with Barclays and Lloyds, but then the Japanese banks get totally split apart in the structure. And it's probably, I suspect, because of the difficulties of restricting oneself to relatively few connections in these graphs. Anyway, to sum up, I'd just like to say how much I enjoyed reading the paper, and I'm sure it's going to prove to be very influential in the field of extremes. Thank you.
Congratulations. I think you have made a wonderful paper. I'm pretty sure this paper will have many children, and I think this will be the beginning of really a new subject in statistics. So I think this is great. I will just focus on one. There are many things, so I could stand here for quite a long time. But since I have limited time, I've chosen just to hit on one particular issue, which I think might be worth considering. There is something called an abstract independence model, and this is the definition of it. So it's sort of, it's sort of something that does independence, and it does at least the semi-graphoid is the important thing. It does these 4 axioms. It's symmetric in A and B. It has sort of a decomposition, weak union, and a contraction thing. And these four axioms there are known as the semi-graphoid axioms. And these are, and if that independence model has to do with probabilistic, standard probabilistic conditional independence, these 4 things are satisfied. Sometimes we can go a bit further, and we also have a graphoid, and it also satisfies this 5th thing. So one thing I was wondering, what about this extremal threshold dependence? Does it do? Can it be? Is it an independence model in this sense? And this is actually quite easy to see. It is. So here is the threshold independence. You have these variables xk, which are when you condition on an extreme event in the kth variable, and they define it as this happens if this is for all k, that you have this conditional independence. The conditional independence to the right is standard conditional independence. The one to the left is this threshold conditional independent, if you like. And then you show actually in the paper that it's enough that it exists for some value of k rather than for all k. And by using the second characterization, it's actually quite easy to see that this thing is actually following the semi-graphoid axiom. So it does everything that standard probabilistic conditional independence does, even though it's a different concept. That's one thing, that the graphoid is a more subtle, and I think maybe graphoid is not always fulfilled, but sometimes for nice models, graphoids are. And in this case, you see immediately you have a problem if D is the empty set, because if you then have these connections there, then suddenly you would need to have a way of saying conditional independence given the empty set. And that we saw actually how that could be done, but in the paper it's not done. And I think somehow that has to be added to the theory to make it completely coherent. And then the question is, when you have graphoid properties, this is not always, but it's a nice thing to follow up. Now, one thing that was what I just thought was that these 4 semi-graphoid axioms actually makes it possible to define any conditional independence models and Markov models on directed acyclic graphs. So once you have an independent structure satisfying these things, you can actually start doing directed graphical models rather than undirected. And I was wondering how one could do that, and I don't know exactly what you should do. What you need is to look at conditional extremal models. So you need to have something like a regression, and maybe because the Hüsler-Reiss is so closely related to the Gaussian, you could actually describe a Hüsler-Reiss regression type model, how the extremes is affected by other extremes, and this is into the causal one that you also mentioned in the talk, but I guess not so much in the paper. So I think that you need this conditional distribution, and or maybe it's not the conditional distribution, maybe it's just you could just say the ratio of these lambda functions, so that you would have a factorization where you on top had lambdas with a child and its parents, and in the bottom. So essentially, you refine them recursively by combination Markov kernels, and because of the semi-graphoid axioms, you have the usual story about equivalence of local and ordered and global Markov properties with d-separation and all that stuff, because in the paper that we wrote with Philip down there in 1990, we realized that since the proofs didn't use densities anyway, we could just make it abstract proofs. So this is actually an abstract theorem that this is correct. And if this were true, for example, you might have things like if a DAG is perfect, if all parents are married, you get the same thing as in your paper, for example, for trees. But you might actually get new models for a thing like that. By combining one of your models for the first variables 1, 2, and 3 with a third model that defines the conditional distribution of 4 given 2 and 3. And that's where I will stop. This was just a reference. Thank you.
Raj Bansali, Imperial College and University of Liverpool. I was interested to see the use of AIC for model selection. It seems to me, however, that AIC can or would lead to over-parameterized model in that situation. Whether or not this is known is a question that's worth investigating. And should one consider the use of generalized or extended criteria where the penalty term is allowed to change and maybe approach infinity at, say, log as in Schwarz's criteria? So it's really a brief comment. I'm not at all an expert in the main area of the paper. But it seems to me AIC should be useful for model selection, but its use needs to be explored.
There have been 8 written contributions. I'll read them to some extent. So the first one is David Cox, Nuffield College, Oxford. This impressive paper deals with extremal problems in a graph theoretical context. Some emphasis lies on the graphical structure itself. In the wide-ranging discussion of extreme values, in a hydrological setting, the system of observational points is usually to be regarded as given, and the interest lies in extremes of a stochastic process defined over that set of points. An exception was connected with the setting up of a rain gauge network for a river basin in southwest England, Moore et al. 2000, where the area was divided into smallish squares, all of which had at least one gauge, and some had many, to allow the exploration of dependencies on different spatial scales. What design issues are implicit in the present paper?
Extremal problems in a hydrological context may involve minima, as in the study of arid and semi-arid river systems, or maxima, as in the study of floods. Reservoir systems need study of both extremes. Some of the properties of large systems, extreme cases being, for instance, the Amazon and the Ganges, have relations described by Horton's laws. Initially empirical relations between positions in the graphical system and flow. The connection with fundamental issues of statistical mechanics was explored by Rodriguez, Iturbe, and Rinaldo in 1997. Extremal problems and graphical structures underpin these hydrological situations, although with quite different emphasis from that of the paper. Do the authors see fruitful links? There's a second discussion by Dr. Ivanovs of Aarhus University. I would like to point out that the methodology described by Engelke and Hitz has applications beyond extreme value theory. Essentially, the authors define conditional independence and then also graphical models for a homogeneous radon measure, lambda, on the positive orthont exploding at the origin. Homogeneity is the key property, allowing one to extend the usual notion of conditional independence in a certain subspace of product form to the whole space. Importantly, such radon measures are central not only to extremes, but also to stable levy motions and related objects, including stable random measures, processes, and distributions. Certain similarities between Max and some stable theories are discussed by e.g. Resnick and Kabluchko. Stable levy motions appear in various limit theorems supplementing Brownian motion in the cases when, for example, heavy tails are present. Importantly, a d-dimensional stable motion is characterized up to a drift parameter by an alpha homogeneous radon measure on Euclidean space r-dimensional Euclidean space with alpha between 0 and 2. The ideas of Engelke and Hitz apply with some minor changes in this setting as well, thus leading to graphical models for stable motions and stable distributions. As in extremes, this alpha homogeneous radon measure, restricted to some set bounded away from the origin, has a clear interpretation. It gives the distribution of jumps from the jumps of S of the d-dimensional stable motion restricted to the set, times their rate. Thus, conditional independence is defined not for the value of the stable motion S at fixed times, but rather for the jumps on every scale assembling into the motion S, which relates Levy-Ito decomposition of a Levy process. Okay. So I'll read part of the next discussion. So the second half is rather technical. The first half, congratulations to the authors on a fine endeavour. Oh, I'm sorry. It's by Phyllis Wan of Erasmus University Rotterdam. Congratulations to the authors on a fine endeavour bringing together two exciting areas. This opens a door for extreme value analysis to the vast literature of the graphical modelling approach. In the paper, the defined framework and the theoretical results are based on the assumption that the tail spectral density of the random vector studied exists and is continuous. This type of assumption is not necessary in the canonical graphical model analysis, and in some way it can be restrictive. A main target for graphical models is to analyze in high-dimensional spaces where data naturally become sparse and concentrated. This could result in either asymptotic independence, which has been shown to be prevalent in real data, or point mass concentration on the spectral measure. One may raise the following questions. How can this assumption be verified in data? How robust is the model estimation process to the violation of this assumption? What would happen in boundary cases where asymptotic dependence between dimensions is weak? In case of asymptotic independence, are there possible ways, for instance, augmenting or transforming the data, such that the theory and methodology of this paper can still be applied? And for this last question, the discussant then outlines a possible strategy, which I won't discuss here. Okay, so a contribution by Linda Mahler of HEC, Montreal. I congratulate the authors on an interesting and inspiring contribution to multivariate extreme value theory. I would like to issue a challenge on graphical models for tail distributions. It seems that an important and natural next step would be an extension of the developed methodology to the setting where the random vector with Pareto margins is asymptotically independent. That is, the setting where the exponent measure places mass on lower dimensional faces of the cone, and where the factorization of the multivariate Pareto density according to a connected graph is no longer possible. Under such setting, Wadsworth and Torn propose to look at the joint tail probability decay rate under different fixed marginal growth rates. And there are some rather elaborate calculations or equations, and the discussant then suggests that it may be possible to define an alternative motion of conditional sub-asymptotic independence for extremes, which in the bivariate setting enjoys a desired homogeneity property. Okay. So there are 4 further contributions, 3 of which are quite technical, and I won't discuss them. So the last one I'll discuss some of. Okay, so in multivariate extreme value theory, distributions. Oh, I'm sorry. Chen Zhou, Erasmus University Rotterdam. In multivariate extreme value theory, distributions in the domain of attraction are often characterized by conditioning on the L-infinity norm exceeding a high threshold. Although using the L-infinity norm provides a symmetrical approach for all dimensions, it also leads to difficulty for defining conditional independence in extremes. The paper by Engelke and Hitz solved this difficulty by first considering conditioning on one specific dimension exceeding a high threshold, and then showing that conditional independence in extremes does not depend on the conditioning dimension chosen from the conditioning set, proposition 1. This beautiful mathematical result paves the way for introducing graphical models for extremes, in which conditional independence is a key building block. The first highlight of the Engelke and Hitz paper is to establish a Hammersley-Clifford type theorem in the context of extremes, theorem 1. This result provides a generator for building new models for multivariate extremes with rather high dimension and complex dependence structure. Yet without raising the computational burden of statistical inference. The second highlight of the Engelke and Hitz paper is that the graphical structure can be recovered from the data without prior knowledge based on combining the minimum spanning tree and a greedy forward selection. My comment is regarding the 2 assumptions in the statistical inference, section 5. Firstly, all separators are single nodes, i.e. we have a block graph. Secondly, the size of cliques is at maximum 3. These 2 assumptions are certainly sensible as a first step towards statistical inference. However, breaking those assumptions will quickly increase the computational burden. Firstly, if the separators contain multiple nodes, say m nodes, all cliques including such separator have at least m plus 1 dimensions. Applying the maximum likelihood method to such cliques will be cumbersome. Secondly, when m equals 1, there is no need to estimate the conditional density of the set of separators, while for m greater than 1, such estimation is needed. Last but not least, if the size of cliques exceed 3, then the complexity of the greedy forward selection procedure rises rapidly. The current successful result in figure 5 may be attributed to the fact that both the true graphical structure and the allowed graphical structure in the greedy forward selection are restricted to having cliques with size less than or equal to 3. And the discussant then comments on an application of the work. So the 3 further discussants, so there is one by Christian Robert. So his comment is about the radial decomposition of multivariate extreme value distributions and the choice of norms for the usual graphical models to be considered. I won't go into the details. And there is a discussion by Valérie Chavez Desmoulins of University of Lausanne, and one by Nicolas Meillet and Olivier Wintenberger of Sorbonne. Thank you very much.
So first of all, I would like to thank all the discussants and in particular the proposer and the secondant for the detailed contributions and very interesting contributions indeed. And yeah, we are probably not able now to go into detail on all of these points, but we'll try to do so in the extended version of the paper later on. So yeah, there are indeed very interesting points that are raised, and I tried quickly to group them in some groups as far as I was able to. So one restriction that was mentioned several times is the restriction of this positivity of the density of the exponent measure. And this relates to the question of asymptotic independence and asymptotic dependence. It also relates to the question on which faces of this orthant we have mass. It's a very complicated question in general because there are 2 to the d minus 1 of these faces. So in higher dimensions d, there are many possibilities where we can have mass. And it's true that in our paper we do only consider the case where we have a density on this whole orthant, meaning that we don't have a mass on the lower dimensional densities. So one solution one could think of is to have actually a first step here to first try to select the subfaces of this orthant where we have mass. There are already some works that exist in the literature, and then model the density on these subfaces with such a sparse extremal graphical model. Because on these subfaces, again, it's just the same problem but in a lower dimension, and we can try to model on this lower dimensional subface the density by extremal graphical models. This, of course, does not include all possibilities of asymptotic independence. It's a very huge, a very large class of possible structures that we can see if we have asymptotic independence. And I agree that something like the Haffen and Thorn model in connection with graphical models could be a more subtle solution to this. So I'm very happy and we're very delighted that Kirsten actually pointed out that this notion of extremal conditional independence can be extended to independence or asymptotic independence. So this makes it somehow much more natural so that we can have also graphs that are unconnected. We can maybe think about, instead of estimating trees, we can estimate forests where we have unconnected components, and this opens a whole new world of possibilities, I think. So yeah, that was a very nice contribution. Then there were a couple of comments about the restriction of the assumption of block graphs, so decomposable graphs where we have singleton separator sets. I agree that this is somehow a restriction because it restricts the class of decomposable graphs. We did this mostly for being able to construct general extremal graphical models by combining those distributions on lower dimensional cliques. But of course, in general, we would like to be able to estimate and infer and learn the structure of more general graphs. And I think one thing that I pointed out in the end would be to look at these Histlerized distributions and try to define an extremal graphical lasso to estimate not only these block graphs, but much more general graphs. This might then even be non-decomposable graphs. But then, yeah, one is somehow restricted to this class of Hüslerized distributions, but which in the class of fully extremal dependence is already quite flexible. But maybe there are other ways of including other families on more general graphs. So, yeah, this I cannot answer now, but I think it's an interesting question for future research. And we also saw this in the application for financial data, that maybe there actually one would like to have something more flexible to model these dependencies that might not sufficiently be explained by block graphs with clicks of small dimension. Then, of course, this was mentioned that there are connections to semi-graphoids, and I think many other notions in graphical models, in the theory of graphical models, that we are possibly not aware of, and I think there's a lot of expertise in that field that might now be, or try to be, translated to the world of extremes. And I think there's a lot of things that we can still analyze, we can still learn from this field, or learn from each other. And yeah, one point that is very valid, I think, is to think about directed versions of these graphical models. And I also think that for like these simple tree structures, we probably don't get any new factorizations. But once we think about non-decomposable or this diamond-shaped graphs, then possibly there are different factorizations that we can obtain. And yeah, I think it's kind of a nice extension of this works. Well, there were also some mentions of links to other fields and other works on extremes and graphical models, and links to other places where these homogeneous measures appear. So one link was this Levy measures, or stable Levy measures, where we indeed have a similar object. So we have also a random measure with density that has this homogeneity property. And yeah, I think it would be very nice to see how these graphical model ideas actually also translate to the cases of Levy motions or other places where these homogeneous radian measures appear. Yeah, I think for now this is what I would like to say, and as I said, we'd like to thank all the discussants again, and we hope to reply in much more detail in the extended version of the paper. Thank you.